So here is an LED, a light emitting diode. It's a diode. That's the important thing here. It emits light. There are other diodes that don't emit light, but they all behave the same way, except that this one emits light. Does that make sense? No? Well, you're stuck with what I just said. You put power to the LED, to the diode in this case, lights up. But if you reverse the electricity flowing through the LED, it doesn't. The diode blocks the electricity from flowing backwards. The diode only wants to see electricity flowing in one direction. Diode lets electricity flow only in one direction. It's like a check valve. But if you apply enough electricity to the wrong way through the LED, electricity does flow. And the way it kind of does that is you've got a little piece of silicon, and it's full of electrons, right? Ooh, look at all those electrons. And if you apply enough electricity, what's going to happen is eventually one of them is going to squirt through backwards through the diode. It's going to fly through it. While that electron is flying through, it might hit another electron. And if it hits that electron, it's going to go flying off, and both are now flying through the silicon. And then that one might hit two, and another couple of electrons are flying through. And you can see it sort of builds up pretty quickly. This is called avalanche breakdown, the point where a diode will start to conduct electricity in reverse. Now, you might notice here there's a certain amount of randomness or chance as to how much electricity is going to flow through. If this electron didn't hit anything, well, you're only going to get one electron running through it until another one decides to try and squirt through because of all the voltage that's been applied. Or it might hit 100 million electrons on its way through, and suddenly you get a giant burst of electricity. This randomness is actually useful. It's used to generate random numbers. It's used to create white noise, which is what this little electronic kit that I bought off eBay does. And here, at the very beginning, Q1, this is an NPN transistor. Normally, these other Q2, 3, and 4 are also NPN transistors, and normally electricity flows from the base through the emitter, which is the leg that has the arrow on it, in the direction of the arrow and out. That arrow represents essentially a diode. But if you look at Q1, it's been wired up in reverse. Power is coming through backwards through the diode here, through the emitter and out the base. And because there's a certain amount of randomness to how much electricity is going to be flowing through it, we have our random noise, or our white noise, or entropy generator here. The rest of this circuit is just amplifying it because it's a very tiny signal here. This this second transistor Q2, that's going to make it a little bit stronger of a signal. This third transistor amps it up even further. This little 1 nanofarad capacitor is going to filter out all the high frequency noise that's there. So that way we only have stuff that we can hear, because this is a white noise generator. And I happen to have 2 of these kits, and so I'm thinking I'm going to build this one, but I'm going to leave that out and take a look at what kind of noise is getting through. See if we can see some of the higher frequency noise generated through this thing. So once it's through its second transistor, or well, actually the third, but once it's through the second amplifying transistor, now we have a direct output to the signal pin here, but it also taps a little bit of the signal off and goes into this fourth transistor to amplify the signal further, so you get something strong enough that can drive a small speaker and you can listen to the white noise. That is the white noise that this circuit is generating. And now I will attempt to move the camera. Ah, you did it again. You did it again. Oh, is it still recording? Oh, that's interesting. Yeah, this is really professional here. Okay, bear with me. There is the oscilloscope. So that signal output is going to the oscilloscope while the audio output is going to the speaker. The yellow line is the signal. The purple line is a fast Fourier transformation of that signal. It's basically showing you the different components of the signal. So if there's like a 10 hertz signal or a 100 hertz signal or a 10 kilohertz signal, it'll show up here, and you can sort of figure out what the component is by, you can see here it's a 2.5 kilohertz per division. That means those vertical lines, each one represents a space of 2.5 kilohertz. So this first block is 0 to 2.5 kilohertz, 2.5 to 5 kilohertz, all the way up to 25 kilohertz, which represents about the range of human hearing. But you can see here, and all the white noise, the most of the signal here is in the first 5 to 10 kilohertz here that's being generated by this. It falls off pretty quickly. That is that 1 nanofarad capacitor doing its job. And we can actually zoom in a little bit more. So 1 kilohertz per division. So now we've got 10 kilohertz across the bottom here, and you can see within the first 4 or 5 kilohertz is where all the fun stuff is happening, and it really starts to die off over there. So that is the white noise generator. And it actually works. That's pretty cool. Oh yeah, and then if the noise is too loud, you can just come in here and little volume control. That's what the this poorly drawn variable resistor here is doing. It controls how much of the signal is going up to the 4th transistor to amplify it. Cool? Cool.